Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the upcoming test. So that's index laws and scientific notation. So remember, when you have an expression like this, the number that's written larger is the base, and the number that's written smaller, the second number, is called the index, power, or exponent. So index laws are all about laws involving these powers. So there's 7 such laws you need to know. So let's start at the first one. This says, if you multiply bases, you keep the same base and add the powers. So if you have something like x to the power of 8 times x to the power of 3, the law says that you keep the same base and add the powers. 8 plus 3 is 11. Now, if you have an expression like this that has pronumerals or letters and numbers, what you need to do is do them separately. So to do something like this, we would do the numbers separately. 3 times 5 is 15. Then we do the x's. So that would be x to the power of 7 plus 4 is 11. And the y doesn't have anything to multiply by, so we just write it by itself. All right, the second index law says when you divide bases, keep the same base and subtract the powers. So if you have something like y to the power of 8 divided by y, remember that y and y to the power of 1 are the same thing. So we would keep the same base and subtract the powers. 8 minus 1 is 7. So again, if you have an expression to simplify that has both numbers and pronumerals, do them separately. So here we would go 30 divided by 12. You can simplify on your calculator. It's 5 over 2 or 2.5. So we've done the numbers, now we'll do the pronumerals. X to the power of 4 divide x to the power of 2, keep the same base and subtract the powers. All right, the third index law says when you have a power to another power, keep the same base and multiply the powers. So if you have something like x to the power of 6 to the power of 3, you keep the same base and multiply together the two powers. So x is the base, 6 times 3 is 18. So the fourth index law says anything except 0 when raised to the power of 0 gives 1. 0 to the power of 0 is undefined. You put it in your calculator, you will get an error. But 1 to the power of 0 is 1, 2 to the power of 0 is 1, negative 5 to the power of 0 is 1, and so on. Now, if you have an expression to calculate like this, 7x to the power of 0, so here x doesn't equal 0, you need to make sure you respect the rules of BIDMAS. So it goes brackets, index, then division and multiplication. So what I'm saying is this is 7 times x to the power of 0, but BIDMAS means I do the index first. So this thing here I've circled is 1. So the answer to this is 7 times 1, which is equal to 7. All right, the fifth index law says if two things are being multiplied and you raise it to a power, just raise the first thing to that power, raise the second thing to that power. In other words, the power of the product is the product of the powers. Note the difference between 3 and 5 here. In 3, this is b is a power, so we have 2 powers. In 5, b is a base, so we have 2 bases here. So if you have something like this, 3x in brackets to the power of 4, you have to raise both the 3 and the x to the power of 4. People always seem to forget in this situation to raise 3 to the power of 4. So 3 to the power of 4 is 81. You can just use your calculator for that, and then you have to raise x to the power of 4 also. So if we have something like this, we need to use a couple of index laws here. So firstly, we need to go negative 5 squared. When you put negative 5 squared on your calculator, you need to put it in brackets like this, otherwise you're going to get the wrong answer. Negative 5 squared is positive. Squares are always positive. So negative 5 squared is 25. X squared squared is using index law 3, keep the same base and multiply the powers. And then we also need to raise y to the power of 2, and we're done. All right, the sixth index law, very logical. If you have a fraction to a power, just raise the top, the numerator, to that power, and raise the denominator to that power. So if we have z over 7 cubed, all we do is raise the top to the power and the bottom to that power. 7 cubed is 343. So to simplify something like this, We raise the top to the power and the bottom to the power, but to raise a to the power of 4 to the power of 5, we actually also need to use index law 3. So to do that, we keep the same base and multiply the powers. To raise b cubed to the power of 5, we keep the same base and multiply the powers. All right, the last index law concerns negative indices. Basically says if you have a negative index, you can move it to the bottom of the fraction, but write it with a positive power. So something like x to the power of negative 8, just put it on the bottom of the fraction and write it with a positive power. So if you have a more complicated expression like this and you're asked to write it using only positive powers, anything with a positive power goes on top. So 2 is 2 to the power of 1, it goes on top. Y has a positive power, it goes on top. The negative powers go to the bottom, but you write them with a positive power instead. So that's all of the index laws. Now let's look at a question involving many index laws. So we're going to have a go at simplifying this expression, writing our answer in index form, and we need to use multiple index laws in order to do that. So let's start with this expression here. The 2 is outside the bracket, so it's not being raised to the power of negative 2. So x cubed to the power of negative 2, I need to keep the same base and multiply the powers. Then y to the negative 4 to the negative 2, a power to a power, keep the same base, multiply the powers. So this expression here is just something to the power of 0. We know that that's just 1. So I can just replace that with 1. Now to expand the brackets here, to get rid of the brackets, I need to use the fractional index law. So I just raise the top to the power, so keep the same base, multiply the powers, and I raise the bottom to that power. Keep the same base, multiply the powers. So when we're multiplying fractions, you can just multiply the tops, multiply the bottoms. So to multiply the tops here, there's nothing to multiply by 2, so I'll leave that alone. X to the negative 6 times x to the power of 12, we keep the same base and add the powers. There's nothing to multiply by y to the power of 8, so I'll leave it alone. On the bottom, 1 times y to the power of 9 is just y to the power of 9. So now I can simplify further because I have y's on the top and the bottom. So that will just give me 2x to the power of 6. Now to simplify the y's, I keep the same base and subtract powers. 8 minus 9 is negative 1. So to write this with a positive power, I would just move the y to the bottom and change its power to positive. And that is my final answer, can't be simplified anymore. So let's have a go at this question here. Here we're solving, we're actually finding a value of x that makes this statement true. And in order to do that, we're going to need to use our index laws. Now, because of index law 5 on the previous slide, we know that 5 times 2 to the power of x, I just raise the first thing to that power and the second thing to that power. But hang on a minute, 5 times 2, this thing here is just 10. So I can rub this out and replace it with 10. So from index law 5, it's actually true that if you multiply two things together with the same power, you can just multiply the bases and keep the power. This is going to be very useful in solving this equation because we can replace 5 to the x times 2 to the power of x with 10 to the power of x. So we have 10 to the power of x times 10 equals 1,000. But hang on a minute, 1,000 is just 10 to the power of 3. Let's rewrite this as 10 to the power of 3 so everything has the same base. Now we know from index law 1, if you have the same base and you multiply them, you just add the powers. So 10 to the x times 10 to the power of 1, keep the same base and add the powers. This is just 10 to the power of x plus 1 equals 10 to the power of 3. This makes the equation really simple. Because each expression has the same base, i.e. 10, then the powers must be equal. We must have that x plus 1, the powers are equal. X plus 1 equals 3, so x just equals 2, and we're done. All right, now we're going to move on to scientific notation. So scientific notation is how we write really large or really small numbers in a convenient way. We always write it as something times 10 to the power of something. The number that goes in this box is always a number between 1 and 10, and the number that goes in this box is always an integer, a whole number that can be positive or negative. So when you're asked to write numbers in scientific notation, you will sometimes be asked to write to a given number of significant figures. Rounding to significant figures is very similar to rounding to a given number of decimal places, except we count numbers before the decimal point this time. So this probably doesn't make a lot of sense. Hopefully it will after an example. So I'm going to write this number here in scientific notation. So the first thing we need to do is locate the decimal point, which would be here. For a whole number, it's just at the end of the whole number. So to find the number that goes in the first box, I just keep moving this decimal point until the number's between 1 and 10. If I move the decimal point to here, the number becomes between 1 and 10. In fact, it becomes 2.705362. So that goes in the first box. Now, scientific notation is always times 10 to the power of something. The number that goes up here as the power is the number of places we've moved the decimal point. So I moved it 6 spaces, so I put a 6 here. So this is correct scientific notation, but I haven't yet rounded to 3 significant figures. So what I need to do is round this part of the number to 3 significant figures. So when rounding to significant figures, numbers before the decimal point count. So this 2 counts as a significant figure. The 7 counts as a significant figure. So this is 2 significant figures. Now, for the third significant figure, I need to go to the next one and use the rule 5 or more raise the score, 4 or less leave the mess. That's the same rule as when rounding to a certain number of decimal places. So because this is 5 or more, I raise the score. I increase the previous digit by 1. So to 3 significant figures, it's 2.71 times 10 to the power of 6. This is basically saying that this number is about 2.71 millions, because 10 to the power of 6 is a million. All right, I'm done with that one. Let's now look at this really small number. So it's a similar process. The number that goes in the first box, number out the front, is this number when it's made to be between 1 and 10. So if I move the decimal point from here to here, then it becomes between 1 and 10. The number just becomes 3.98414. So that goes out the front. So it's always times 10 to the power of something. So the power of 10 is how many places I move the decimal point. So I moved it 1, 2, 3, 4 spots. So I put a 4 up here. But I need to be conscious of this rule here. This power is positive when the number's large, like it was here, but it's negative when the number's small. So this number is small, it's smaller than 1. Because I moved the decimal point the other way, I moved it right this time, it's actually a negative 4. So any number that basically starts with 0 will have a negative power, and any really large number will have a positive power. So this is correct scientific notation. Now I'm going to round to 3 significant figures. So once again, significant figures, you do count digits before the decimal point. 3 is a significant figure, as is 9. Now, for 8, we need to check the next number. 5 or more raise the score, 4 or less leave the mess. This number is 4 or less. We don't raise this number by 1. We just leave it as it is. We leave the mess. We just get rid of all that. So to 3 significant figures is 3.98 times 10 to the minus 4. So what this is saying is that this number here is about 3.98 10,000ths. All right, let's now look at a worded problem involving scientific notation. So a nanometer is 10 to the minus 9 meters. That means 1 billionth of a meter. So we want to know how many of these make up 2.4 kilometers. So hopefully you can see when we're saying how many of these make up this is a division problem. We can't just divide 2.4 by this, however, because we have kilometers and meters. They need to be in the same units. So 2.4 kilometers, let's convert to meters. So it's 2.4 times 1,000 or times 10 cubed. So that's 2.4 kilometers in meters. We simply divide that by 10 to the minus 9 meters because we want to know how many of these do you need to add up to get this. So you can just put this in your calculator. I'm just going to use index laws to simplify this. So we have number and some bases, so we'll do the number separately. The 2.4 has nothing to multiply by, so I'll leave it as it is. Now the rule for dividing bases, because this means division, you keep the same base and you subtract the powers. 3 subtract negative 9 is actually positive 12. So this is saying there are about 2.4 trillion nanometers in 2.4 kilometers. All right, thank you so much for tuning into this video. Best of luck for the test, but I'm sure you're going to ace it. This has been the luckiest maths teacher in the world. Have a great day.